Okay, here's our video today. Why mitochondrial DNA only comes from the mother. And we know mitochondria is the powerhouse of the cell. You've probably heard that even in middle school. That's where energy comes from. It's where ATP, the energy molecule, adenosine triphosphate, that's where it's primarily made in the cell. And mitochondria, they do other things as well. They help with calcium levels in your body. They regulate calcium levels, and they regulate cell death, apoptosis, which I have a video for somewhere in there. And we'll talk about endiosymbiosis also later in this video. But by the way, it comes from the mother, not just in humans, right? In nearly all animals, even insects. So let's write that down. Get my pen ready here. Maybe we'll use red. So, the mitochondrial DNA, right? Where should we write it? Right over here. Mitochondrial DNA, that's how it's written, comes from the mother only in almost, there are some exceptions, all animals. So, not just humans, even insects. And again, there is some exceptions. So, what this means, in simple terms, right? The sperm does not contribute to any DNA, mitochondrial DNA. There's the simple answer. So let's get a clean page here. And there you see a cell, a crude, simple picture of a cell, which they show in textbooks. So again, the sperm does not contribute. So that's from the father, right? It's mitochondrial DNA. And there's a reason for that. So let's look at a picture of it. So during fertilization, when the sperm enters the egg, right, it does not contribute its mitochondria because its tail falls off. You can see right here. Let me get my pen working. Right? Very simple answer. You see in the tail, in the mid place of the tail, that's where the mitochondrial DNA is stored. So when the sperm enters the egg, only the head enters the egg and the tail falls off. So that's it. That's the simple reason why mitochondrial DNA from the father is not passed on. So everyone has their mitochondrial DNA from their mother. Well, there are very, very rare exceptions where it could actually enter the egg. And also in humans, and most animals, right? We could have hundreds to thousands per cell. I mean, if you go back to that crude picture, let's go back to that picture. Right, and here's the picture, right? So the mitochondria, you see four. Well, there's more than four. There's hundreds and thousands, like I said. The brain, just think about the energy the brain needs. So there could be even 10,000 and so forth mitochondria, all from the mother. And so it's important to know that mitochondria, of all the organelles, besides the chloroplast, because in plants, chloroplasts have their unique DNA also, but mitochondria have unique DNA. Right? Every other part of the cell has its nucleus DNA, which is 99.9% of your total DNA. So that 0.1% that you get from your mother is the mitochondrial DNA. And this leads to the idea that mitochondria had a symbiotic relationship billions of years ago, entered a prokaryotic cell billions of years ago. I have a link, I'll put a link below, on endiosymbiosis, which explains that. And then, you might be asking, well, is there a problem if the paternal and the maternal mitochondrial DNA came together? Well, yes, there could be complications, right? They could be competing. This could lead, if the paternal mitochondrial DNA entered the egg, you could lead to dysfunctional energy production. because, again, they're competing. So having maternal lineage of mitochondrial DNA ensures efficiency, it ensures stability, and that's how it's happened in natural selection. And again, like I said before, I should write these numbers down. So most of your DNA, that's the nucleus DNA, right? The nucleus DNA makes up 99.9% of you. And then you have also now your mitochondrial DNA from your mother, which is 0.1%. All right, that's our video today.